All right, here we go with the Chapter 5 Homework 2 review. The average this week was 9.4 out of 12, a little bit lower than last year, so maybe some things we need to shore up before next week's exam. So welcome back from spring break. Hope you all had a good one, and we need to get back into chemistry, so let's get right into it. So all these questions are requests from students. There were a lot of similar types on the homework that we had some difficulty with, so these are all good ones to go through. And really, it's just several variations, many variations really of stoichiometry problems. And the key factor there, the key step we have to be able to do is convert to moles of usually a reactant, and then from there we're going to determine some other aspect of the chemical reaction, whether it be moles of product form or grams of product. And there's just all kinds of different ways of doing that, but it really revolves around the central key idea of moles and how to convert into and out of moles, especially at this point using mass. But as we'll see in the newest stuff that we're doing, there are other relationships involving moles as well that we're going to have to use. So getting into the questions, the first couple are going to be a little bit more of conceptual type, I suppose, not necessarily doing actual calculations, or at least not very in-depth calculations, but they're again dealing with the concepts of moles of reactants and limiting reactant especially, which is a big topic in this homework assignment. All right, so we have, in this problem, equal masses of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Now, one thing we didn't tell you in this problem, but it ends up not mattering because you'd get the same answer either way, is that hydrogen gas is H2. We'll learn this a little bit later on, how all of the elements have sort of their standard states, as they're called, and for most of the for just about all of the gaseous elements, the nonmetals especially, those are going to be typically diatomic, so H2, O2, N2, even the halogens, F2, Cl2, and so on. It doesn't really matter in this case if you didn't do that correctly. If you just said that hydrogen was H and oxygen was O, you'd still come to the same conclusion either way. But we're going to do it correctly and say it's H2 and O2. And we want to know which of these substances is a limiting reactant if equal masses are combined to form water. So we're going to take H2 and O2 and combine them to form water. So really, the first step in most of these stoichiometry problems is going to be to produce a balanced equation. And especially a lot of the ones that we had difficulty with, we didn't give you the chemical equation directly. We kind of just gave you some words in the problem that helped you figure out what it would be. And so this is one of those where we're telling you H2 and O2 are reacting to form water. We know the chemical formulas for all of those. And then we just have to put coefficients to balance. So don't forget to balance the equation once you write out the reactants and products, because very often you're going to have coefficients other than one that are involved. So we want to balance this. It looks like we need a 2 in front of water and a 2 in front of hydrogen. So 2H2 plus O2 goes to H2O. As I said, you may not have realized at this point in the course that hydrogen is H2 and oxygen is O2, so you may have also written out 2H plus O going to H2O. And while that's not technically correct, it would still get you the same answer in this question, so it doesn't matter if you did that or not. All right, so we want to know if equal masses are combined, which substance is limiting. If we're combining equal masses, we can basically assume whatever mass we want, or we can do it in abstract. So we're going to, think about, a convenient number to use, basically. All right, so we're going to look at this problem and figure out what's a mass of reactants that we can assume. It doesn't really matter what we do, but let's pick one that's convenient just to make our math easier. So if we look at the molar mass of all of these, of the two reactants, for hydrogen it's around 2 grams per mole. For oxygen it's around 32 grams per mole, 2 times 16, so we don't have to be terribly precise here. So we're going to look at this, and let's say if we assume 32 grams of each reactant. Again, I'm just picking a number that's convenient. I don't really say that this is the only way to do it. But if we assume 32 grams of each reactant, or just any mass amount, but I like 32 because that means we have easy numbers. So 32 divided by 2 would be 16, 32 divided by 32 would be 1, so we'd have 1 mole of oxygen, 16 moles of hydrogen. And so if we want to find out which one's the limiting reactant then, which substance is limiting is what this is asking, meaning limiting reactant, we need to find moles of each reactant. So the moles of hydrogen would be 32 grams of hydrogen So now we're just going to follow the approach that we always use to figure out limiting reactants. Again, not being too terribly precise with molar masses. We don't really need to be in this problem because we're not calculating anything. So we get 16 moles of hydrogen, but then remember, to figure out if it's a limiting reactant or not, we calculate what's called the stoichiometric ratio, or at least this is the way that I prefer to do it. So we take that number 16 and we divide it by the coefficient, which is 2, and we get 8. So the stoichiometric ratio for hydrogen, if we're assuming 32 grams, is 8. We'll do the same thing for oxygen. 32 grams of oxygen convert to moles. Remember, the mass amounts don't tell us anything from a stoichiometry standpoint. We always have to convert to moles. So we have 1 mole of oxygen, and then its stoichiometric ratio is going to be 1 divided by the coefficient, which is also 1. And so the one that's the smaller of the two is going to be the limiting reactant. That's clearly O2. And so the correct answer would be, I accidentally crossed it out when I was trying to underline, it's choice A, oxygen is limiting. Okay? So oxygen gas is limiting reactant in this case. This one is nonsensical. You can't have a product be the limiting reactant, so that one we could remove right away. Some of you may have been tempted to pick E because we didn't give you the masses, but we just told you the masses were equal, so we could have assumed any mass we want, and no matter what mass we assumed, if we had gone through these steps of converting to moles and finding stoichiometric ratios, we would easily determine that oxygen is the limiting reactant in each case. All right, so that one was a little bit more abstract, and same with this next one. It does involve calculations in this case, but it's looking at this picture here, and we're showing the reaction between AB2 and B2, and so it's showing where we're starting with, what we're ending with, and it says if 5 moles of AB2 reacts with 3 moles of B2, how many moles of B2, if any, would remain unreacted? Okay, so we are going to go through the steps first of finding a balanced equation. So we have AB2 and B2 are the reactants. And if we look at the reactant side, we see that we have 2 of the orange spheres together, so that means B2 is, so B is going to be orange in this case. And then we have a black sphere with 2 orange spheres, that's going to be A, B2, so that means A is black in this case. And we need that information because if we look at the product side, we see that the new product that's formed is this guy here, all of these, which are AB3. So that's going to be the product. We don't see any other products. We see some extra in this picture. We see some B2 that's unreacted, but we're not actually going to use that to solve the question. It just shows us that the only new product that's formed is AB3, so we're going to put that as our product. So I think in this problem, the tricky part was getting the chemical equation, because again, we didn't give it to you, directly. But we have AB2 plus B2 going to AB3. AB3 is our only product formed. And then we just have to do the same steps as last time and figure out which the limiting reactant is. All right, so here we're talking about individual molecules, but they're proportional to moles by Avogadro's number, so we can either do it with molecules or moles. Let's do it in terms of molecules because the approach is the same. So the molecules of AB2 on the reactant side, 1, 2, 3, 4, 5, 6, and the stoichiometric ratio, then we have to balance this equation. We haven't done that yet. So I got ahead of myself because I got excited about doing this problem. All right, if we balance this equation, we need to do, let's see. This one's a little bit tricky to balance, but I think we could do a 2 there and a 2 there would get us a balanced equation. 2AB2 plus B2 going to 2AB3. So that gives us 2 A's on each side and 6 B's, correct. Okay, so these are the coefficients. 2 in front of AB2, 1 in front of B2, 2 in front of the product. And we find the molecules of each on the reactant side by looking at this picture on the left. So we have 6 molecules of AB2, and the stoichiometric ratio for AB2 is going to be 6 divided by its coefficient, which is 2, which is 3. And then if we do B2, which is our other reactant, we look at the reactant side, we have 1, 2, 3, 4, 5. And the stoichiometric ratio for B2 is going to be 5 divided by the coefficient, which is 1. And that equals 5. I think I lost my pointer, so hang on a second. Alright, that's probably better. Now I have a laser pointer so you can see what I'm pointing at better. Alright, so as I said, we have a coefficient of 1 in front of B2, so when we divide that by the coefficient, we get 5. So that means that this is our limiting reactant. So we're going to have some B2 left over, but we need to figure out how much that is. So it's not going to be 0 in this case. If we're going to figure out how much is left over, we figure out how much is consumed. So the moles of B2 that are consumed is going to be determined by the limiting reactant. So we have, or molecules, I guess, if you want to think about it that way. Let's do molecules since we're talking about individual molecules, but you could interpret it as moles too. It work the same. So the molecules of B2 that are consumed are going to be, we have 6 molecules of AB2 reacting. And then from the balanced equation we have Alright, I've been doing this problem all wrong because I'm an idiot. So I didn't read it closely. So here we're reacting 5 moles of AB2. So I counted the number that were in here. That's probably where I got confused the same way many of you did. So don't look at the pictures to figure out how many molecules we have. We're actually looking at 5 and 3 because that's what it tells us in the problem. So reading the problem is important, and I skipped that step, which is why I screwed up. So we're going to fix some things here. So we instead have 5 moles of AB2, and so if we find the stoichiometric ratio for AB2, that's going to be 2.5, and then we have 3 moles of B2, so we take the moles, or molecules I guess, of B2 divided by the coefficient, we get 3. This is still the limiting reactant because it's smaller, not smaller by as much. So then we do the same thing. So I just had the wrong numbers, I apologize for that, but now that we have the correct numbers, 5 molecules, or 5 moles I guess, of AB2. So in this problem we're only using the picture to find the balanced equation. Once we know that, we're not going to look at it anymore. So we have 5 moles of AB2 and 3 moles of B2. And so we want to find the moles of B2 that are consumed. We have 5 moles of AB2. And then we use stoichiometric ratios. 1 mole of B2 is consumed for every 2 moles of AB2 that reacts. So we're consuming 2.5 moles of B2, and we started with 3. That's the wrong 3, but that's the 3 there. So the moles of B2 that are excess we started with 3. We reacted 2.5 with our limiting reactant. So we have 0.5 moles left over, and that should be the correct answer. All right. So I guess I'm still in spring break mode, and I can't do stoichiometry anymore. But once we have the right numbers here, 5 moles of AB2, 3 moles of B2, we just use the balanced equation, and at that point the pictures don't matter anymore. Alright, so that one did not go well, but get better. Alright, so now we're getting into a few different types of stoichiometry problems. So the first couple, again, were largely conceptual, although that last one involved a little bit of calculation. Now we're going to just go through the different types of stoichiometry problems we have. And the first couple are going to be what are called mole-to-mole calculations. So here we're given a balanced equation, 2a plus b goes to 3c plus d, purely fictitious. And we're told that we have 3 moles of A, 2 moles of B, and we form 4 moles of C. We want to know what is the percent yield. So in these types of problems, if everything is given in moles, we don't have to worry about any conversions. We don't have to use molar masses or any other conversion factor to convert into and out of moles. We just use the number of moles given to us directly. All right, so if we have to first figure out what the limiting reactant is to figure out what our theoretical yield is. So we're looking for percent yields. We should always think about where we're going. So we're looking for percent yield in this reaction. We're told that we're formed 4 moles of C, so that's going to be the theoretical yield, and we're specifically talking about product C here, which is what's given to us in the problem. Actual yield divided by theoretical yield, though. Jeez. I will eventually come back to life. Actual yield divided by theoretical yield. times 100. And we're given the actual yield. We're forming 4 moles of C, so that's our actual yield. And we have to figure out what the theoretical yield is and then multiply everything by 100, the ratio. So we're going to find out what the theoretical yield is to be able to get the percent yield at the end. So theoretical yield, again, is determined by the moles of limiting reactant. So we have to figure out which of these two is limiting reactant. We gave you moles of A, moles of B, so one of those two is going to potentially be our limiting reactant. We have to figure out which one it is. So remember, to find limiting reactant, we just take the moles of each reactant and divide it by the coefficient. The moles of A is just going to be 3.0, so in this problem we're directly given moles. And so the stoichiometric ratio for A is going to be that number 3 divided by its coefficient, which is 2, which gives us 1.5. And then if we do the same thing for B, the moles of B, again in this problem directly given to us, we have 2. And its stoichiometric ratio is going to be the number of moles divided by the coefficient, which is just 1 or 2.0. So this is going to be our limiting reactant because it has the smaller stoichiometric ratio. And then we're going to use the number of moles of A to figure out how many moles of B could theoretically form. So we're going to find the theoretical yield of C using that. So the moles of C, which is our theoretical yield, the maximum amount that could form in this reaction, is we start with limiting reactant, which is A. And then we use coefficients to find the moles of C. And here we just stop at moles because the amount that we're given is in moles. So we don't need to calculate grams. We can't calculate grams here because we don't have molar masses. So we just use the coefficients in the chemical equation. So we want moles of A to cancel out. We want to find how many moles of C would form. And so C has a 3 in front of it, so the coefficient is 3. A has a 2 in front of it, so the coefficient is 2. And so that tells us that we would get a maximum of 3 times 3 times 3 over 2, which is 4.5 moles of C is our theoretical yield. So then we're going to put 4.5 moles as our theoretical here in the denominator. Multiply by 100, and we get 4 divided by 4.5, which is 88.9. I guess we'll just do 89% to keep the sig figs correct. 89% yield for C. I think a lot of these questions were probably multiple choice questions. You'd have to pick the right answer. I'm not going to go through all the answer choices because we're just getting numbers in most of these. So in this case, we get 89% yield. Whatever is closest to that would be our answer. So again, it's using limiting reactant to figure out our theoretical yield, and then we divide actual by theoretical. And in this case, as I said, it was a mole-to-mole problem, so we don't need to worry about any conversions into or out of moles. We just use the moles directly, but same approach, using stoichiometric ratios to find limiting reactant, and then mole ratios from the chemical equation to find moles of product that are formed. All right, and then this next problem here is also a mole-to-mole problem, but this time we have real substances. So we have reaction of N2 and H2 to form NH3, and we want to know how many moles of N2 will produce 34.2 moles of NH3. And I think, this question, a lot of us missed it. It was one of the ones that we had the lowest success rate on. And I think probably what happened is a lot of us just tried to do too much. We tried to assume that we had to use molar masses, assume that we had to do all kinds of conversions, but in reality here we don't. We just need a balanced chemical equation, and then we just need to use the number given in the problem and go right from there. So we have to balance the equation of N2 to H plus H2 to form NH3. All right, and again, maybe not the simplest one to balance, but we have 2 nitrogens on the reactant side, so we put a coefficient of 2 there. We have 6 hydrogens, so we put a coefficient of 3 there. So a pretty simple one to balance, but we had to make sure we get those ratios correct. And then we want to know how many moles of N2 will produce 34.2 moles of NH3. And so again, this is a mole-to-mole problem. We're giving you moles of one substance. We're asking you to find moles of another. So we don't even need molar masses in this case because we don't have to worry about grams either as a given quantity or as something that we're trying to solve for. So we're looking for the moles of N2 that are required to form 34.2 moles of our product. So in this case, we're starting with moles of product. We don't have to worry about limiting reactant here because we're not giving you amounts of 2 reactants. We're not asking you, we're giving you amount of product that can form and figuring out how much reactant we need for that. So we have 34.2 moles of NH3. I think this was a problem that had variable numbers, so you might have had a different number of moles of NH3 to start with, but the approach is the same. You start with your moles of NH3, and then we're looking for moles of nitrogen, and even if that wasn't our stopping point, we know at this point we can use mole ratios to figure out about how many moles of N2 we have. So we want moles of NH3 to cancel, moles of N2 in the numerator, so we have a coefficient of 1 in front of N2, a coefficient of 2 in front of NH3, we just divide it by 2. And here we have moles of NH3 canceling out. Moles of N2 is in our numerator, and that's the quantity we're getting to. Sorry, tablet froze. Here we go. So moles of N2 is what we're getting to. That's what we want. So we just stop there. 17.1 moles of N2. So I suspect that a lot of you try to make this more difficult than it was. But that's all we had to do there, was just use mole ratios to figure out how many moles of N2 would be needed to form this many moles of NH3. So you needed the balance equation. Without that, you would have been stuck. But once we have the balance equation, it's a relatively simple conversion. All right. Next variation on this one is we're going to start dealing with masses now. So Fe3O4 plus carbon to form carbon dioxide and iron. So again, words to translate into a chemical equation. So the number of moles of carbon required to convert 23 grams of iron oxide to products is, so let's see, we have a gram amount here, we're given grams, and we're looking for moles. Okay, so this is going to be a mass to mole conversion. We're trying to keep track of what type of problem it is. So there's these different variations, but really what the variations sort of dictate for you is just what steps you need to take as part of your conversion. It doesn't, the key concept is still the same. We have to get into moles of one of our substances. We use mole ratios to convert to moles of another substance. So that key linchpin step is always the same, but we have different things on the ends of that to either convert into or out of mass in some cases. So here's a mass to mole. We're giving you mass of a reactant. We want to find out the moles of the other reactant that are required. So it's a couple steps here. All right, so what we're going to do is first write a balanced equation. So we have Fe3O4 with carbon, which is just C, to form carbon dioxide, CO2, and iron, which is just Fe. So we need some coefficients. We have 3 irons, so we're going to have to put a 3 there. We have 4 oxygens, so we need a 2 in front of CO2. We have 2 carbons, so we put a 2 there. So it's 1 mole of Fe3O4, 2 moles of carbon, forming 2 moles of carbon dioxide, 3 moles of iron. What really matters in this problem is the coefficients in front of our reactants, because that's what we're dealing with. So we want to know how many moles of carbon are required to convert 23 grams of Fe3O4 to products. So we're looking for moles of carbon. We're given grams of Fe3O4. So in this case, since we're given grams, we have to first convert into moles. We can't just do the conversion directly. So we need to find moles of Fe3O4, and to do that we again use molar masses, same step we've been doing a lot, where we use the molar mass to relate grams and moles. We need the molar mass of Fe3O4, so let me get that real quick, because I didn't calculate this beforehand. Alright, so the molar mass of Fe3O4 is about 231.6, assuming I did that correctly. So 231.6 grams of Fe3O4 per 1 mole. We divide by that so that grams cancel. That gives us moles of Fe3O4. And then what we're looking for is moles of carbon. So if we're going to convert to a different substance, we use mole ratio. So it's going to be 2 moles of carbon, coefficient of 2, over 1 mole of Fe3O4, which is a coefficient of 1. So moles of Fe3O4 cancel. We now have moles of carbon, which is what we're looking for. So we stop there and just convert straight across. So we get 0.20 moles of carbon. I think this was a multiple choice question where the correct answer was either 0.20 or maybe just given as 0.2, but that's the one that we would pick. So again, you have to have a balanced equation, no shortcut around that, but once we have it, we figure out what we're looking for, we figure out what we're given, and we do a series of conversions to get between those two quantities. All right, and then the last couple, I guess 3 or so we're going to do are all mass to mass now. So here we want to know the theoretical yield of bismuth when 373.3 grams of Bi2O3 reacts with excess carbon. So because we're told that it's excess carbon, we already know that Bi2O3 is limiting reactant, so we don't have to do any steps to figure that out. But we do have to balance the equation. So we have Bi2O3. This is actually not too dissimilar from the last one, a reduction with carbon to make bismuth metal, and this time carbon monoxide. So if we have 3 oxygens, we need 3 COs. 2 bismuths, we need 2 in front of there. 3 carbons, we need a 3 in front of there. Okay, so we have to, again, add some coefficients to make sure this is balanced. And we want to know what is the theoretical yield of bismuth. Now, we didn't specify here, but if we don't tell you, or it's not a multiple choice question, we should be looking for grams of bismuth. That should have probably been said more explicitly than it is, especially if this is a numerical problem, which I think it was. So we're going to look for grams of bismuth, maybe not obvious, but that's going to be grams of this product here, Bi. And we have 373.3 grams of Bi2O3. So we're looking for grams of our product bismuth, starting with 373.3 grams of Bi2O3. And this is a mass to mass problem because we're given mass of a reactant, we're looking for mass of a product. So if we want to classify this, it's called mass to mass. And so we start with the mass of our reactant Bi2O3. We need to convert into moles, so again we're going to need its molar mass. We want grams in the denominator, moles in the numerator, so we need to find the molar mass and put that in the denominator. So let me get that real quick. Sorry, hang on a second. Alright, so depending on how precise we want to be, the molar mass of Bi2O3 is 465.96. We could have definitely done less digits than that if we needed to. So that gives us moles of Bi2O3, but what we're looking for is grams of bismuth, so now we need to use mole ratios to convert into moles of bismuth first. So we want moles of Bi2O3 in the denominator and moles of Bi, bismuth, in the numerator. And if we look at coefficients, the moles of bismuth is 2, moles of Bi2O3 is 1, so that gives us a 2-to-1 mole ratio, converts to moles of bismuth. But we're looking for grams of bismuth here, and so we need to use the molar mass of bismuth. So that's from the periodic table. So if we go to the periodic table, we see that the atomic mass of bismuth is 208.98. So we want grams of bismuth in the numerator, moles in the denominator, so that they cancel out. So we're going to multiply by the atomic mass, 208.98. Alright, so we have grams of bismuth. And when we multiply this across, what we should end up with is, let's see, 373.3 divided by 465.96 times 2 times 2.98. Alright, so if I did my math right, what I calculated was from this we would get 334.8 grams of bismuth. And again, this was a numerical question, so the numbers you might have had would be different, but it's the same series of steps. So this is a typical mass-to-mass stoichiometry problem. We start with mass of a reactant, we calculate mass of product, and the series of steps are we're going to use molar mass to convert to moles first, mole ratios to convert to moles of the other substance, in this case our product, and then again molar masses or atomic masses as it is here to calculate the mass of our product. Alright, so that's going to be a pretty typical problem that we do of that type. Alright, so that's a mass-to-mass stoichiometry problem, and then we have a couple others like this. Alright, so there was a typo here, but this should say not XL but XS. But we have 11.9 grams of CHCl3, which is called chloroform. You may have seen that in movies as something that you can use to cause someone to pass out, but hopefully you don't use it for that purpose yourself. So we have 11.9 grams of chloroform with excess chlorine. So again, that tells us that this is our limiting reactant. We don't have to even worry about determining what the limiting reactant is. We produced 11.2 grams of CCl4. We want to know what is the percent yield. So just like before, the percent yield is going to be the actual yield divided by the theoretical yield times 100. And in this case, as is typically the case, if we're calculating percent yield, the actual is going to be given to us. So we're producing 11.2 grams of CCl4, so that's going to be our actual yield. Our theoretical yield is not given to us here, so that's what we're going to calculate. We multiply that by 100. So we need to calculate the theoretical yield of carbon tetrachloride. It's given to us in grams. We want to calculate the grams that could potentially form. We have grams of our reactant, 11.9. So this is going to be another mass to mass type conversion. Okay? So we're looking for the grams of CCl4, which is going to be our product, which is going to be our theoretical yield. How much of this could potentially form if all of our limiting reactant is consumed. So we're starting with 11.9 grams of chloroform, CHCl3, and we have to convert into moles first. So we're going to divide by molar mass, same step as always, to figure out moles of CHCl3. So it's about 119.37 grams of CCl3, so that's the molar mass of CHCl3, sorry. So that gives us moles of that, and then we look at our balanced equation. I don't know why it's balanced with coefficients of 2 everywhere. That seems unnecessary, but in this case we didn't have to worry about balancing it, so we just use what's directly given to us, and it's going to be, we want moles of CHCl3 to cancel, and we're looking for moles of our product CCl4. That's what we're trying to get to here is CCl4. So we see that 2 moles of CCl4 form for 2 moles of CHCl3. This is not the best way to balance this equation because we have all these coefficients of 2 that are not the smallest whole numbers, but it still works as long as it is balanced, and we're so we have that conversion there to get moles of CCl4. Then we have to use the molar mass of CCl4, which is sorry. Let me get that number, 153.81. So again, we're going to use molar mass to convert back into grams, which is our final number. So we want moles of CCl4 in the denominator, grams in the numerator, so that means we're going to multiply by the molar mass of carbon tetrachloride, which is 153.81 grams per mole. All right, so when we multiply this across, we get a theoretical yield of about 15.3 grams. So 15.3 grams of carbon tetrachloride, that's our theoretical yield, the maximum amount that can form. So we're going to put that in here into our calculation for percent yield. So percent yield is the actual yield, which was given as 11.2, divided by the theoretical yield of 15.3, and multiply by 100, and what we get is 73.2%. All right, and I don't remember if this was a multiple choice or numerical question, but that would be the number we would want to choose as our answer, 73.2%. Okay, so for a percent yield problem, you're typically going to be given the actual yield. So this is our actual yield, as we said, which is given to us in the problem, and then we calculate the theoretical yield and go from there. Okay. All right, last one. So we didn't have to deal with limiting reactants in this one either, because we're looking for mass of carbon dioxide when 10.6 grams of butane burns in an excess of oxygen, forming CO2 and water. All right, so again, a lot of clues here to determine the chemical equation. The one that we should be getting familiar with is combustion reactions, which is when we're burning something. So if we're doing a combustion reaction, it's always going to be some reactant that typically is a hydrocarbon, carbon and hydrogen, or sometimes a carbohydrate that has some oxygen in it as well. We add that to oxygen as our other reactant, and we always form the same 2 products for a combustion, which is CO2 and water. We're told that here directly, so even if you didn't know what a combustion reaction was, you could certainly have gotten this one. So we have to balance the equation. So typically we set this to a coefficient of 1. We have 4 carbons, so we make 4 CO2s. We have 10 hydrogens, so we're going to make 5 waters. And then we're going to balance oxygen last. So on the product side, we have 8 plus 5, which is 13 oxygen. So we get a coefficient of 13 over 2 here. If fractional coefficients bother you, we could multiply the whole thing by 2. You don't have to do this for this problem especially because we're just using mole ratios. But if we multiply the whole thing by 2 to get rid of fractions, we get 2 C4H10 plus 13 O2s going to 8 carbon dioxides and 10 waters. All right, so some sizable coefficients here, but whether you use the fractions or don't use the fractions, you'll get the same answer either way as long as you have the ratios correct. So we covered balancing last week, so I'm not going to go through that in detail, but that's the balanced equation, and we're just looking for then mass of carbon dioxide produced when 10.6 grams burns. This is another mass to mass problem. We have mass of a reactant, we're looking for mass of product. So we have mass of carbon dioxide that's formed, we have 10.6 grams of C4H10, that's our starting point. And just like any other stoichiometry problem, when in doubt, or pretty much whether you're in doubt or not, you should do it, you should convert to moles first. So we're not given moles, we're given grams here, so we're going to convert to moles first. 1 mole of C4H10, sorry, I didn't write that very well, is how many grams? That's going to be the molar mass, which is about 58.1, I believe. Let's see. Yeah, 58.12 grams. So that's going to be the molar mass of C4H10 that allows us to convert grams into moles. And then we're figuring out how much CO2 forms. We have to use mole ratios involving CO2. It could be either 4/1 if we started with this balanced equation here, or 8/2 in the one that gets rid of coefficients. Either way, it's the same. So we have moles of C4H10 to cancel out. Oh, I can't write that C4H10 correctly today. Can't do much of anything correctly today. And then we have moles of CO2 in the numerator. So ratios, we have 8 moles, coefficient of 8. We have 2 for a coefficient there, or 4/1 works too. So that gives us moles of CO2, and then finally we're going to do, we want grams of CO2, so we have to again use molar mass. It's a mass to mass conversion. So the last step is going to be using the molar mass of CO2 to convert moles into grams. So that's going to be 44.02 grams per mole for CO2. And so when we work this out, let's see what we get. What I got was, seems big, 32.1 grams of CO2. Let me double check that number because it seems bigger than it should be, but maybe it's fine. That's it. Okay, so 32.1 grams of CO2 would be our answer in this case. Always good to double check your calculator work because that's the easiest place to make a small typo, even if you write out everything correctly. So I double checked, I got the same answer, so 32.1 seems to be right, and that's what you would have chosen for this one, which again, I don't remember if this is multiple choice or numerical, but that's the number we need to get. Alright, so that takes us to the end of this review. As you can see, a lot of different types of stoichiometry problems, but the series of steps are all very similar between them. We're going to be converting into moles, we're going to be using mole ratios to convert one substance into another, and then we just really have to look closely at what the question is asking us to figure out what are going to be some of the final steps we do using that quantity. So we're going to get some more variations on stoichiometry in Chapter 6, probably on Wednesday of this week, will be the last thing we do before the next test. So these concepts of using mole ratios especially are not going to go away anytime soon, so we have to make sure that we're clear on those. As always, the invitation is open. Please come find me in my office if you have any other questions about the homework assignment this week or anything else going on in class, and I look forward to seeing you back in lecture on Monday this afternoon.